Okay, so hello everyone. My name is Antonio Ríos-Vila, and today I'm going to present what I've been working recently this year, which is also part of my master final thesis, which is completing optical music recognition with agnostic transcription and machine translation techniques, a work that I've done with David Rizo, Jorge Calvo-Zaragoza, and José Manuel Iñesta. This work begins with the analysis of the current OMR pipeline, which, as we can observe, starts from a pre-segmented music excerpt with object detection models. Then we get the stuff of the recognized objects through a recognition system that outputs an agnostic encoded output, a text sequence that represents the symbols that are recognized in the music score, which is called agnostic because it represents both physical features of the elements that are in a music state, which are the shape of the symbol and also the position in the staff. However, there is an issue using this agnostic encoding, and it is that despite of being a good encoding for recognition tasks, it is not usable in an end user application. So we cannot say the pipeline is just completed because the results that the recognition system is getting are not exportable to other applications such as Perovio for visualization, Sibelius, and such. So this work is focusing mainly on the encoding part of the optical music recognition pipeline that Understanding Optical Music Recognition defines, which it is to encode that notation given in a graphics language into what is called a semantic language that retrieves all the semantic relationships between the elements of the stuff. Also, it is interesting to explore a little bit more on this step, as the current state-of-the-art encoding systems, also in commercial applications, are actually rule-based systems which have several scalability issues, whether both the agnostic or the semantic encodings are extended, and of course they are also hardly to maintain when we get to the polyphonical case. So we are focusing our research on performing this encoding step with machine translation or more advanced machine translation techniques, which is what we are going to talk about in this presentation. Our main idea is to use two kinds of pipelines or compare two kinds of pipelines. One which makes a direct encoding, so it gets a music stuff as an input and it gets a semantic encoding of that stuff. And also another pipeline, which is our formulation for this problem, that takes an image stuff for the image recognition system. It gets the agnostic recognized sequence for the symbols that are in this stuff, and then this is automatically translated into the semantic sequence in a machine translation process. So the first question that may rise when we make a translation between an agnostic and a semantic encoding is which semantic encoding we should use, as there are multiple ones and it is difficult to choose whether using one or another. So the first idea that we came up with, it was to use MAI or Music XML encoding languages. However, we discarded this option because they are two verbose encodings, as we can observe in this slide, where we need a lot of tokens to represent a sequence, and it is also not very convenient for this verbosity, as it is difficult to align the agnostic encoding sequence with the semantic one. So researching a little bit further, we decided to use hand-drawn kern as our encoding of choice because it has more short sequences, it has a simple vocabulary, it's also easy to align with the agnostic encoded sequences, and the most convenient thing that it has hand-drawn kern is that it can be transcribable to other encodings such as MAI or Music XML with already implemented language tools, such as Perovio, which is something that has to be really celebrated because we don't need the other languages using this encoding to get our results done. So to present briefly what are we doing in our pipelines, first we've got the graphical recognition, which is the current state-of-the-art on optical music recognition in end-to-end systems, which is the convolutional recurrent neural network trained with CTC loss function that has already been mentioned in this workshop, so I won't go a lot on detail on that. And then we are testing 3 machine translation models that we have studied to be interesting in the translation between an agnostic encoding and semantic ones, especially the agnostic and kern vocabularies, which is a data-driven approach, which is called the statistic matching translation model, which generates two kinds of models in a data-driven approach, which is the translation model to get the most probable token given the input sequence and the already predicted tokens in the translation process, and a language model that somehow regularizes the predictions of the translation model in order that they are fluent and somehow to say cohesive with the target vocabulary. And with a search algorithm, it gets the most optimal solution for this translation problem. Then we've got the neural-based approaches, which are the sequence-to-sequence with attention mechanism translation system, which it is a system that with an attention mechanism gets a context vector from the encoder, and it tries to get the most relevant parts of that representation within a decoder to get the prediction of the most probable token given the previous prediction. And its natural evolution, which it is the transformer model, which is currently the state of the art in machine translation, in the machine translation area, which it inherits the structure of the sequence-to-sequence architecture, but it replaces the recurrent neurons with ones called the multi-headed attention ones, which it is a complex attention mechanism that tries to get the interrelationships between the input sequence that is fed into both the encoder and the decoder. And it usually tends to get better representation vectors of the language to make a better translation. So the corpora used for this experimentation was in modern notation. We used first the camera primus, the camera printed image music samples from the Riz dataset, because we wanted to use a printed music score to know, well, a printed music dataset for getting our results and say if the systems were working correctly or not. And as a test case, we use a more real case in optical music recognition, which is a handwritten music corpus, which is the Fondo de Música Tradicional, which has already been presented in this MEC conference, which it is a corpus with less data, but we can use it as, let's say, a more realistic case model to know if our models are getting good or not at their task. So without further ado, I would like to present our results, which are these presented in this slide. On the left, we've got the individual results, so to say how they perform the systems individually. And then we've got the complete pipeline results, where we compare our proposed approaches with the baseline proposed with direct encoding. So as we can observe on the left, we can see that if there is enough data, the transformer model, as it is expected, it gets the best results and the best language model for translation. But when there is lack of data, there is probably more, it is more usable to use the sequence-to-sequence attention model or the statistic matching translation techniques, because they are simpler models and they get with less data a fairly usable translation or language model for translation purposes. But the most interesting results are on the right side of the graphics, where we can observe first that the translation models do not improve the error generated by the graphical recognition step. We can see, for example, in the Primus dataset that they do not get worse or better than a 4 sequence error rate. And in the Fondo de Música Tradicional, they do not get a better error than a 35 sequence error rate, which is also plausible because as we try to get some variance on the input, they need to, well, the test that we finally are doing is how able are they to handle inconsistencies on the input being trained with perfect inputs on their training phase. So also, as we can observe, our proposition, our pipeline works better than the baseline, except the transformer on the Primus dataset, which is something also fairly understandable because the Primus dataset does not have a lot of variance to be handled with inconsistencies in the test case. But when there is not enough data, we can see that the difference in error on the presented pipelines are significantly better than within our baseline. But it was interesting for us to see how many data is it necessary to get the best or to surpass clearly the baseline between our proposition and the direct encoding pipeline. And we made it with the Primus dataset, and as we can observe, this is done around 5,000 samples, which it is really interesting from some conclusions that we may draw. Of course, as we get less data, the translation mechanism are better. So as a conclusion, we are getting our pipelines are more beneficial where there is a lack of data, which is also an interesting scenario where there is cultural message heritage. And it also opens an interesting use case scenario because we do not need so much data to start labeling a corpus with automatic processes, which is something interesting in some use cases. Well, thank you.
Thank you so much. I hope I will not create a loop here, but if you have questions, please raise your hand now or speak up. I'm trying to monitor this here. If someone, or maybe you just want to think about it for a second. And I have actually two questions that I would like to ask. So at the end, you showed how you can kind of, the dependency on how much data you use, you get different results. So my question would be, if we have approaches like we've seen today to synthesize data, it would not be unreasonable to assume that we can basically generate an infinite amount of data. If you have an infinite amount of data, which approach would you recommend?
Well, if we have infinite amount of data, I think the transformer approach would be the best one, because of course we have used a transformer model, which is the state of the art, and we have seen that if we struggle with data, it is not the best approach. But transformer models, of course, in the natural language processing task, they have been shown to be really good when they are pre-trained and then fine-tuned with a corpus. So if you have the opportunity to train your model or to pre-train your model with enough data set, for example, if we have infinite data, we can pre-train the model on that generic data set and then fine-tune it into our target corpus. So I think if we have infinite data, the transformer approach would be the best one.
Thank you. Other questions? Itch, please.
I'm sorry, I might have missed the whole point. So you're assuming that the agnostic output from the OMR may be wrong and it will be corrected when you do the translation. Is that correct?
Well, it's something that you can expect, but you don't have to. So the idea is that the output of the agnostic output of the recognition system will be fed into the translation model as it is. So the ideal state is that the translation model would be able to correct the agnostic input, but it is not something that we have observed in our results. That's why in the presented results, the translation-based pipelines do not get a better error than the line drawn by the graphic recognition pipeline. So it would be ideal, and it is of course something that we want to research in future works. But in the state of the state we are now, it is not possible.
Thank you.
Time for one more quick question.
Oh, sorry. I think it was Alicia first, I think.
Well, I can keep the question for the panel. I don't mind.
Okay, sorry, I forgot how to raise hand on Zoom. I have one quick question. You mentioned earlier in the presentation that the rule-based approaches have problems with scalability.
Yeah.
Can you expand on that a little bit? Like, what exactly are the problems you run into when you do that?
Well, of course, when you've got a rule-based driven system, there is, of course, there are also extensions on both the agnostic on both the source and the target languages, because, for example, hand-run kern can get some extensions. We made an extension that erases or simplifies multi-measure rests, for example. And if you extend both of the source or the target languages, maybe some of your rules get deprecated, you have to update them, maybe you have to redesign the whole system, as for example happened to us transcribing a corpus with plain and easy code and hand-run kern. David is not here to comment his experience, but also in the case of polyphonic languages, where in the polyphonic music or polyphonic representations, also languages get too complex. For example, hand-run kern can get too complex for that, and designing new rules maybe gets a more cost, or also a high maintainability cost that sometimes can be assumed. So yeah, more or less is that.
Okay, I understand. Thank you.